Heavenly Father, we thank you so much for this day. We thank you for the beautiful weather that we woke up to this morning, the cooler temperatures, and God, as we eye we could remind ourselves of the blessings we enjoy and that we could be generous and kind to those who are less fortunate than us. We pray that you would continue to watch over our schools, bless our students, our teachers, bless our families with safety and with good health. And Lord, as we go throughout the day, I pray that we could strive to put forth our best effort, whether it be in class, whether it be on the field, whether it be in the cafeteria, whether it be in the car, whatever we do, whatever we say, whatever we think, God, I pray that that would be uplift to one another and honoring to you. Please bless those of our number who are sick. Watch over those moms and dads who are taking care of elderly parents or sick young people. And pray that you would give us all strength of mind and of character to do your will and to help others see the light of Christ in us. And we pray this all in Jesus' holy name. Amen. St. John Baptist de La Salle, and Jesus in our hearts. All righty. Thank you all. You have a seat, fellas. And let's see here. Where did my picture go? There it is. Y'all are seeing my screens. My screen now. All right. So what we're going to do is we're going to shift gears just a little bit. And last week we had talked quite a bit about word problems with 2x2 systems. So I also need to introduce the notion of a 3x3 system. Okay. That would be where we have 3 variables and 3 equations. Okay. Now to do that, we're going to remember a little bit of the info that we talked about in the last couple of weeks. So I've got these 3 quick little warm-up questions for you. I want you guys to get cracking on them. Numbers 1, 2, and 3 right here, these 3 warm-up questions. And they will not only just remind us of some of the basics that we talked about in the last couple of weeks, but they'll also help us springboard into what we're doing today. Okay, so we got these 3 warm-ups. You guys get working on those. Let's see how my attendance is looking. All right, perfect. Get a little warm air for the hair. How long have you been standing out here? Oh, I never heard you knock, man. Sorry. We've just been rocking and rolling. Here, sit down and I'll zap you. While I'm thinking about it, do you guys have Monday and Tuesday of school next week, or are y'all off the whole week, or what's y'all's schedule? Y'all are off the whole week at Holy Rosary? Y'all are off the whole week at St. Louis? Where's my OLPH guys? Y'all off the whole week? Huh. Bunch of lucky ducks. My parents, my wife and kids are off all next week too. So we will have to forego our early morning class, I reckon. George, we're just doing these 3 quick little warm-ups, and then we're going to get rocking on our new lesson. Now, at this point in the game, fellas, as you're still working on these, efficiency is the name of the game. Okay, what do I mean by that? I mean, I gotta be able not only to know what to do, but to know how to do it quickly enough to get me through a problem like this. Okay, it's like, I imagine if you were running the hurdles on a track team, right? You not only need to know how to get over the hurdle, but you need to get over the hurdle at speed, so that you can keep running the race at your normal pace and keep up with everybody else. So these hurdles will get easier with time the more that you practice your technique, right? Best hurdle runner I ever saw was a girl in my class when I was in high school. She ran and her head never moved. The whole time she was running, jumping those hurdles, it was amazing. Good form can go a long way for you. And so when you guys are working these, I want y'all to have that good form. Don't let your head move, Mossy. Good form indeed. All right, let's talk about this first one here. Grove, tell us what to do on number one. I know we're still working on the others, but hopefully got number one finished.
For number one, I substituted -2 for x, -4 for y, and 3.
Yeah, just a little plug and chug problem. That's no big deal, right? So I like using parentheses to help me keep my signs straight. And then we just work out the arithmetic. Okay, so that's -10. That's +8. So that's -2 altogether. -2 and 9 makes 11. No, -2 and 9 makes 7, doesn't it? What'd y'all get, 7 or 11? That's what I thought. All right, very good, very, very good. Now, for our second example, Mossy, I was picking on you a moment ago, so I'll come back to you and ask, what technique did you use? Substitution or elimination? Or heck, maybe you got crazy and did some graphing. I don't know. Which one do you use? Elimination. Which variable do you want to eliminate? The x variable. All right, so that means I'm going to multiply the second equation by 2 and cancel out my x's. That's going to give me 7y equals 7. So y equals 1. And then I can take that and I can plug it back in, right? So I'll just plug it back into the first equation. So subtract 1 from both sides. I got -2x equals -12. So x equals 6. So I would say my solution here would be 6, 1. That's the ordered pair that would be on both of the lines when they're graphed out. That's the ordered pair that would make a true statement in both equations. All right, anybody get anything different than that? Want to ask any questions, talk about why we did what we did? And did anybody use substitution on that one? Okay, substitution would work similarly, right? If I wanted to get, I don't know, if I wanted to get y by itself in that first equation, for example, I could get y equals 2x minus 11, plug that expression in for y in the second one, and we get x plus 3y equals 9. And now I've got one equation in terms of one variable that just needs to be solved out. So 3 times 2 is 6, plus 1 is 7x, 3 times 11 is -33. And then add 33 to both sides, and what do we get? 42. And divide by 7, we get x equals, how many times is 7 going to 42? 6 times. We get our x equals 6, and then like we said, we can just plug it back in. 6 times 2 is 12. 12 minus 11 equals 1. That's where we, bless you, that's where we get our y equals 1. So whether you're using elimination or substitution, we ought to be able to run with it. I'm talking run with it, okay? Now on this last one here, what do y'all want to do? Eliminate the x or substitute? Somebody say something. Substitute, okay. So add 5y to both sides. And we got 27 plus 5y goes in place of x. So down here, I got 7. I got 27 plus 5y. So somebody's going to have to help me with 7 times. That's going to be 189 maybe. Let's see here. 7x plus 8y equals 43. What's 7 times 27? 7 times 2 would be 140. 7 times 7 would be 49. So that's 189. 35y, 8y, so that's 43y. And then, let's see here. This would be 6, 4, 1, negative. How many times does that go in? So if I subtract 189 from both sides and divide by 43, I get y equals, what'd you say? Somebody's going to help me with my dadgum division, aren't you? It doesn't work out. Negative 146 over 43. Is that as simplified as it gets? I let my calculator out. Oh, well. Let's make sure I didn't mess anything up. 46. I like that. 146. That's negative. And 8 and 5 makes 30. Yeah, there we go. Yeah, I'll take that. Now, that's an ugly answer, isn't it? What do I do with that ugly answer? Plug it in just the same, right? We got a pretty answer over there, x equals 6 on the previous example. Y'all didn't have any problems plugging that in. We should still be able to plug in y equals negative 146 over 43 into the other equation. Let's do that. Let's see here. So what was it? X equals 27 plus 5y, negative 146 over 43. So we ought to be able to simplify this out. So x equals, I have to have screwed something up. These numbers are so ugly, but whatever. We'll try. Let's see here. 5 times 6 is 30. 5 times 4 is 20. Plus 3 is 23. And 5 times 1 is 5 plus 2 is 7. So 730. So negative 730 over 43 plus 27. Oh, good night, America. What's 27 times 43? Have y'all done none of this arithmetic? 3 times 7 is 21. 3 times 2 is 6 plus 2 is 8. And 4 times 7 is 28. 4 times 2 is 8 plus 2 is 10. So 1, 6, 1, 1. So what do I have? Negative 730 over 43 plus 1161 over 43. Oh, and I have to subtract now? Ugh. I cannot believe that none of y'all are going to whip out a calculator and help me do this. Y'all are just sitting here watching me squirm, aren't you? 1161 minus 730. Lewis, you got anything to say? You're being awfully quiet up there, Bubba.
Not really.
431. So 431 over 43. So it looks like my answer would be a nice, beautiful 431 over 43, comma, negative 146 over 43. Now, you know what I'm going to do? Just because I don't know if I would have given you that as a warm-up question with such an ugly answer. I'm going to check it real quick. Y'all know how to check your work on these types of things without having to go through the horrendous process of plugging that back in? Google. Excuse me. What do y'all think? What should I do? Oh! Yeah, what we're gonna do is I'm gonna search system solver. And usually there's a nice little applet that we can pull up. So if you're doing homework and you want to check your work and Bob's not being very helpful, right? Or maybe you're doing an even numbered problem, just Google systems of equation solver. Wolfram's got a good one here that typically comes up first on the list. So all you really need to do is just enter in a few of the equations. Now, read me off, Alex, what my first equation was. Three. All right. What was my second equation? All right. I don't have a third equation. Oh, dump. Okay. I don't know why they put me in a 4x4 system solver already. There we go. All right. So those were the two. Is that right? Okay. Okay. Oh, now, brown cow. Aren't those the answers I got?
Yes.
Oh, okay. Now you're not feeling so smug, are you? Okay, so that's a crappy warm-up example, but it is a good example of where you're not always going to get a nice answer, and you can just grind it out with a little bit of arithmetic if you watch your step, if you're careful. I know that looks like a bunch of hogwash, Degum, because I was squeezing it all in there, but it is the solution to the system. It's just something that we got that was rather ugly. That's okay. We're not always going to get pretty answers. So, questions on the warm-ups? Okay. Did you notice on number one, it was one equation in terms of three variables? What was that third variable? Z. Okay, that's the natural progression. So when we move up from a 2 by 2 to a 3 by 3, instead of an ordered pair of x comma y, we're going to be looking for an ordered triple, x comma y comma z. Yeah.
So what would we have to do?
Typically, you bump it back and you go w, x, y, z. And then you wouldn't have to, an opportunity of looking at it graphically speaking at that point, because you can't graph. So we can't very easily graph in 4 dimensions. And then for 5 dimensions, of course, that's getting way above my pay grade. But in 3 dimensions, this is what it looks like. And you guys do not have to take these notes down. I just kind of want you to use your eyes. But what we're visually looking for when we are solving these bigger systems, like instead of a 2 by 2, a 3 by 3 system, we go from 2 dimensions to 3 dimensions. Now, what I do want you to write down is the following, that a linear equation of 3 variables, you know, we talked about the one that has x, y, and z. A linear equation of 3 variables, his graph is not a line, it's a plane, P-L-A-N-E, plane. So the graph of a linear equation of 3 variables is a plane, whereas the graph of a linear equation of just 2 variables, you guys have been practicing this year, is a line.
Are you going to show us how to graph that?
You know, you could do it. It's rather challenging, but we could do it. So, like, supposing that there is, and I've always forget this without looking it up, but imagine there's this third axis, and I don't know why I'm dotting it, because we can make it solid, not a problem. There's this third axis that comes out of the paper, okay, pointing out towards us. Now, it's very challenging to draw in 3 dimensions on a 2-dimensional piece of paper, right? But like if I have an x-axis, as I normally do, a y-axis, as I normally do, and then I introduce a z-axis, okay? If I introduce this notion of a z-axis, that's just where my third coordinate would come from. So like if I wanted to graph the point, I don't know, let's say 5, 2, 3, okay? Then all I need to do is come out 5 on the x-axis, so that's 1, 2, 3, 4, 5. Up 2 on the y-axis, 1, 2. So right there, would be how we would graph it in 2 dimensions. The point 5, 2, you know, imagine that z-axis is not there. That's it. There you go. You got a graph. But then the z-axis, we've come out into that 3rd dimension. How many units? We come out 3 units. So 1, 2, 3. And let's see if we could do this. Oh, that's lousy. Let me try. Graphing in 3 dimensions is always challenging for me. I don't know if you guys ever do much of it. There we go. That doesn't look too bad. And here would be where our point is. Right? Where you would go in the x direction 5, you'd go in the y direction 2, you'd come in the z direction 3, and there would be your point. You can kind of see it's like a rectangular prism that's drawn there. So like in 3 dimensions, we're looking for where do those 3 planes intersect. So if you've got 3 equations, one in terms of 3 variables, another in terms of 3 variables, and then the third one in terms of 3 variables, you're looking for the point of intersection there between those 3. Now, just like when we talked about in linear systems, sometimes there are special cases, right? There might be a case where we call it an inconsistent system, right? James, how many solutions does an inconsistent system have? Yeah, none. No solutions, right? That's because there is no point of intersection. If the 3 lines were parallel, the 2 lines were parallel in our old examples, here in these new examples, that'd be like having our 3 planes all parallel, or where they're intersecting in certain ways, but not in the way where there's a point in common on all 3 of them. Remember, to be a solution, you got to have a point in common on all 3 of them. Then there's also the special case of infinitely many points in common, infinitely many solutions. There's a point in common, there's a point in common, there's a point in common, there's a point in common. So there are illustrations of what's called a dependent system as well, remember, where we talked about maybe all 3 of the planes are exactly the same, and there's infinitely many points of intersection, right? So again, graphically speaking, you guys are not going to be graphing in 3 dimensions, okay? That's an Algebra 2 skill all the way. But what you are going to be doing is you are going to be solving a system by hand that looks just like this. Here's our first example. This is what we're going to work together on for the next 10 to 12 minutes. Okay. Now there's nothing different. Listen to me. There's nothing different in how we're going to solve this system. Technique is going to be exactly the same. You're going to be canceling out a column. You're going to be using substitution. You're going to be doing the same techniques that we've done before. It's just since it's a 3x3 system, we're going to do it more than once. Okay, did you hear me on that? So because it's a bigger system, our job, watch my hands here, is to take it from a 3x3 system down to a 2x2 system. And then we're on comfortable ground like what we were in the warm-ups, and we know that to solve a 2x2, we take it down to a 1x1. Okay, so write your system down here if you don't have it written down already. Notice that it's in standard form, isn't it? We've got our X column, our Y column, our Z column, and then our constant column. Everything's lined up nice and neat. And the instructions here say for us to please use elimination. So that's what we're going to do. I'm going to teach you how to do that. Again, it's going to be structurally, it's going to be exactly the same as what we've been doing. Okay. Now, I'm feeling generous. Candiato, I'll let you pick. You want to eliminate one of the variables, Jack. Which one do you want to eliminate? You want to eliminate Z. All right. So what we're going to do is we're going to pick two equations, two of the three. Pick you a pair of equations that you think would be easy for us to eliminate Jack's variable of Z. Okay, George, what do you think? Pick a couple of equations. You can pick 1 and 2. Okay, very good. So here's what we're going to do. We're going to pick 1 and 2. And we're going to come down here and we're going to eliminate Z. Now, I got plenty of room. Hopefully, you got plenty of room on your paper. So here's what I'd like. We're not going to mess with the original system. Let's rewrite those first 2 lines again. And we're going to eliminate Z. So we got 2x plus y plus z equals 4. All right. Now, what do I need to change about one of those equations? What do you think there, Jake? All right, we could change the sign of all of the terms in one of those so that we could get our z to be negative. Some of you might say, well, Coach Morgan, can't we just subtract everything? And absolutely you could. I usually forget that, though. I usually say, yeah, I'll subtract, and then I end up adding one of them, okay? But if I physically change the signs, check this out. If I physically make that a negative, make that a positive, make that a negative, and make that a negative, I'm not going to screw it up. I'm not going to mess it up. So just like Oxley did, now I changed the signs on the top, sorry, Jake. But just like Oxley said, if we change the signs of everything in one of the equations, Z ready to eliminate. And you tell me, what are we left with? What do you think, Andrew?
Negative x plus 2y.
No. Tally everything up. Tally everything up. So what do you got? Negative x and 2x makes how many x's?
X.
So we got x, good. What else?
Plus 3y.
3y, good. What else? Equals 1. Perfect. So what do we have now, Jack McBee? What is that result? That's one equation, and how many variables are in it? 2. So fellas, you and I have talked before that if you've got 2 variables, you need what? 2 equations. How are we going to get another equation? Here's where the creativity comes in. Who wants to be creative and tell me, how am I going to come up with another equation in terms of x and y? What do you guys think? Go for it, Nate. All right, so substitution, what do you mean by that? I don't agree, and we're not going to use substitution, but tell me kind of what you were thinking. Okay, so have x in terms of 3y. Oh, okay, actually, I do agree with that. I think that might, if you subtracted 3y, 1 minus 3y, and go up in here and plug it in somewhere. Now, the reason I said I don't agree is because the instructions say use elimination. But what Nate's doing is he's barking up the right tree just with different instructions. Okay, so that's what you would do for substitution. Somebody help me eliminate. I want to figure out another equation in terms of x and y using elimination instead. What do you think? Go back to where I was being generous with Candiato. What did I let Candiato do? He picked the first and the second equations. Tiago, what do you want to pick? The second and the third one. Okay. So in other words, if we pick a different pair of equations and repeat the process of eliminating z, we're going to have another equation in terms of x and y. And therefore, we will have taken it successfully down from a 3x3 to a 2x2. All right, so let's do what he suggests. He said, hey, pick the second and the third equation. So again, I've got plenty of room, so I'm gonna come down here. We're gonna rewrite that. We got 2x plus y plus z equals 4. We got 3x plus 4y plus 3z equals -1. Now, if I want to eliminate z, Quentin, what do I need to change about that first equation? All right, not just the signs, but I also need to change that coefficient. I really would like that top equation to have a -3 in front of that z. Man, that'd be nice. So let's do that. Let's multiply that top equation by -3. Okay, so that's going to be -6x. That's going to be -3y. That's going to be -3z. And that's going to be -12. And what I've done is I've now produced an equivalent equation there. Quentin, go ahead and I'm going to cancel out my z's. You tell me, what do I got left? Perfect. And now, look at what we got, fellas. We've got, well, I wrote that rather small, didn't I? We've got two equations in terms of two variables. All right, we got two equations in terms of two variables. Now this becomes a problem, just like what you guys have handled last week, where you say, okay, I'm off to the races now. I can solve it however Coach Morgan lets me solve it. Not a big deal. Why don't we do this? X plus 3y equals 1, and -3x plus 1y equals -13. What do you guys think? Eliminate the x's or eliminate the y's? If I eliminate the x's, I'm going to keep the numbers manageably small, relatively small. If I wanted to eliminate the y's, I'd need to multiply everything on the bottom equation by -3, and I'm going to have -39, and not that I can't deal with that, but those numbers are bigger, and I like smaller numbers if I can get away with it. So multiply 3 on the top, and what do we get? 3x, 9y equals 3. That's an equivalent equation. Set it up, knock it out, roll it out, rawhide. We got 10y equals -10, or y equals -1. Do you feel like I went through that too quickly? Okay, remember, we're trying to jump those hurdles at speed. It's okay at practice to trip over one of those hurdles, isn't it? Do you guys run track? Do y'all get to do track in middle school? Okay, it's okay for me to kick a hurdle every now and then. All you do is set it back up and try again. So if you screwed the pooch on that one in blue, if you said, dadgummit, I messed something up, set it back up and try it again. Okay? All right, now, Joey, what do I do with y equals -1? Now I plug it back in over here in blue somewhere, preferably. Look, I could do this. Let's plug it right there. Y is the same thing as -1. So that's x equals 4. Okay. Now I've got two pieces of the puzzle. And now we can come back to what Nate was saying a minute ago. And now that I know x equals 4 and y equals -1, heck, why don't I just pick one of my 3 first original equations over here and just plug that in? 4 for x, -1 for y. I still don't know what z is, but we could solve that out. Y'all help me. What is that? 6 plus z equals 3, so z must be -3. Z equals -3. And how do you think I write my answer up, class? As a what? As an ordered triple. It's underlined up there in blue. Ordered triple. So what do I think? 4, comma, -1, comma, -3. Okay. Now, graphically speaking, what did we just find? We just found the point of intersection of those 3 planes. Remember, the graph of a linear equation of 3 variables, like that right there, that first equation, x minus 2y plus z equals 3. If you graph that in 3 dimensions, which you are not responsible for doing, but if you let some computer program on the internet do it for you, you would see a plane, an infinite set of ordered triples. And then if you graph that second equation, you would see another plane. And if you graph that third equation, you'd see another plane. And those 3 planes would have intersected at one point. And that one point is what we just found the coordinates of. 4, comma, -1, comma, -3. Okay? So solving a system of 3 equations and 3 variables using elimination, let me recap for you. You pick 2 equations, eliminate one of the variables. You pick another 2 equations, eliminate that same variable. Then you take that 2 by 2 system and go to town on it, just like you did last week. Okay? Now that's elimination. Substitution, something that we'll work on tomorrow, works a little bit differently, but as Nate pointed out, it's really going to be getting the same answers just through a different way. Okay? You can solve 3 by 3 systems. All right? Our 3 techniques are graphing, substituting, and eliminating. Once you get into Algebra 2, you'll learn something called determinants and Kramer's rule and matrix operations. Those will be your other 2 techniques. And those are a lot quicker because those involve, a lot of times those involve calculators and computers that can run the numbers for you. That's how Wolfram Alpha did this one, or the previous example. It just ran the numbers doing matrix operations. And so you guys will learn that in Algebra 2. But do you have any questions from today's lesson? All right, hopefully you're not a little shell-shocked. What we're going to do is tomorrow we'll go through and we'll learn about some substitution, and then maybe we'll look at a word problem. We'll see. But in the meantime, live Jesus in our hearts. All right, thank you so much, fellas. Y'all take care. Have a good day.
Wait, I have a quick question.
Oh, go for it. Lay it on me.
So when you pick your 2 equations to solve and then another 2 to solve, does it matter which ones you pick?
No, you could pick numbers 1 and 2. You could pick numbers 2 and 3, or you could pick numbers 1 and 3. As long as you eliminate the same variable both times, then you'll be set.
All right, thanks.
Yeah, you're welcome. Y'all take care, fellas.